So today we're starting to do nonlinear dynamics basically with very simple systems. Most of them are coming from mechanics, right? You know, calculus and mechanics, they're like invented at once, hand in hand, right? And so in the old times, people didn't distinguish between, you know, someone who's doing maths or physics because they're doing them together, right? Okay, so that's what we're starting to do today. So there you go. Okay, let's start writing, right? So nonlinear dynamics, I can call ABCs in nonlinear dynamics. Okay, and we're gonna do basically ODEs. And first, we're gonna look at ODEs with the variable being on just in R. Okay. So the simplest example and one of the most fundamental ones is the harmonic oscillator. So the story goes like this, you know, imagine you have a little spring and in its rest position, it would be somewhere there, but then of course so there is no gravity, nothing going around, okay, so this is its mass, okay, but doesn't matter because it's not, I'm not taking it in the gravity field. Okay, so there you go. Okay, so let's say we have the axis here. So we're measuring the displacement of this thing. So let's put 0 when it's in rest position. So this would be the rest position. Okay, or the equilibrium position. And then if we pull it, right, you know, it goes a little bit off and then it will have a restoring force F that brings it back, right? So this is given as a minus K and then X. X, it has a sign plus or minus, depending if it's on the right or left of 0, right? Of the origin. K, it's called, it's the elasticity constant. So it's a constant that is, you know, coming from the qualities of the material, right? So elasticity constant, it's a constant, it's a number, right? And it's taken to be positive anyhow, so no point to make it negative. All right, so now, you know, how do we describe the motion of this thing? Well, we describe it with what you did in high school, so I'm not going over what you did in high school, you know, is the wonderful F equals M times A, right? So A is the acceleration of this thing, and F is what, you know, forces are acting on this object, right? So this would be equivalent to M is its mass, A is the second derivative of the displacement, right? I could put it with a vector notation, right? Just to give it an orientation left or right if you want, and then minus Kx are the forces, okay? So now when we discuss this one plus or minus as X is positive or negative, we're going to end up with one equation of motion that looks like this, d2x, a dt2, and then because M is positive, it's a mass, right? These are all, you know, physical objects. We can say, okay, so this is K over mx equals 0, or, okay, if we denote this K over M as omega squared, right? So this is a positive number, so we can introduce this notation, and then we're going to use the dot notation for derivative, right? So this is derivative in time, just to make sure that you guys understand what I'm saying. So basically what we have here, we have a wonderful harmonic oscillator, ODE. This is the simplest ODE linear of the second order that you do actually in your ODE intro course, okay? And just a second, guys. Go.
Okay.
Start doing this. Stop doing this kind of stuff. It's worse if you're trying to sneak. Okay, there's my son. He finished school and he's like,
I'm just trying not to.
it's all right, fine. Just go once and then it's done, you know?
Yes.
Okay. All right. Yeah, teaching at home. Huh? Okay, so now I do remind you how these were solved, right? It was like you have to do the characteristic equation. So it was r squared plus omega squared is 0, and then you're solving plus minus I omega, and then you're ending up with, you know, we can write this x of t as a cos omega t plus b sine omega t is the general solution, where a and b are some constants. Okay, so for every a and b, we have a different solution. Now, a and b, of course, are linked to the initial conditions. So now if we want to do physics out of it, right? So let's write it again. Okay, and in physics, the solution is usually given in the form x of t is a cos omega t plus phi naught. Okay, that's how they are taught in physics, and you can see obviously that is a trig function. And now these a and phi naught are related to the initial conditions. So let's put some initial conditions. So let's say x in 0, which is, call it x0, right, is given. And then we have x dot in 0, the initial velocity, let's say is v naught, okay? Now, if we do this and we calculate what a and phi naught are, right? So I'm gonna let you do this, okay? So do it. Okay, it's just algebra, okay? You're gonna end up that, you're gonna find out that a is root of x naught squared plus v naught squared over omega squared, and tan of phi naught is minus v naught over omega x naught. Okay, so this is the simplest, ODE second order that comes from physics. You know, everybody does this, and there is a reason why this ODE is so fundamental, or this model of the elastic oscillator, is because any system, any mechanical system that is near its equilibrium point, it will do these little oscillations. It will have its, little vibrations near the equilibrium. And this can be proven actually, all systems, think about, that my favorite one is with a ball at the bottom of a top. At the bottom, there is the equilibrium position. If you just shift it a little bit, that ball will start, just right there, just doing the little oscillations. But in principle, all systems are doing this, in chemistry, you name it, right? So things, near the equilibrium will oscillate if that equilibrium is stable, by the way. Otherwise, they might just be the other way around. Like if you put the ball on top of a hill, right? It's like a golf ball, right? And you're on top of a hill and you just give it a little push, it will just go away, right? So that's an unstable equilibrium. We'll talk about this. But near a stable equilibrium, if you give it a little push, it will just start jiggling there like little, as I said, little vibrations. And those are modeled exactly by this kind of, elastic ideal systems, if you want, harmonic oscillators. All right, so this being said, now can we understand this oscillator, in a kind of a different way, rather than just writing the solution and then, I don't know, just making a wave, oh, let's draw it. Can we comment on the behavior of more than one solution? Because here, for every initial condition, you'll have a solution, right? They're all kind of doing the same, but, I'm coming back to maybe we can represent them differently. And indeed we can, if we introduce the notion of energy. Okay, so first I'm gonna define what is a simple mechanical system. Okay, so a simple mechanical system, and maybe we'll talk more about this. I will not divert the course into a mechanics course, though. You know, I'll try to stay in math. Okay, is a system that is defined by its potential energy and its kinetic energy. So, is a system defined as a sum of kinetic and potential energies. And to put you at ease, I will always tell you what are those. Okay, so for our system here, for this one, let's call it 1. For 1, we're going to define T to be the kinetic energy. And this is, we're going to define it to be 1/2 x dot squared. And the potential energy, I'm going to define it to be, so I'm defining them. I'm telling you what they are. Okay. So is, well, actually, here, let's do it like this. So let's write this one in its original form. It was mx2 dots plus kx equals 0. So that's the one I'm referring to, because that's the mechanical one that comes from the modeling. Okay. So then if I do this, then I can write kinetic energy as maybe some of you did it in school. So is the mass times velocity squared. Okay, and the potential energy is 1/2 k times the displacement squared. And then we define the total energy, E total if you want, to be the sum of the two. Okay. And here what little miracle is happening and where it leads is, that's more important, right? So this is the original system. Okay, so I repeat, M and K are given. There are some constants that are positive. And then E, the energy, which is defined in terms of displacement and velocity, dx dt, was defined by your teacher to be this quantity. Okay. All right. And now, you know, I will prove to you miraculously that the energy is conserved along any solution of this system. Okay, so first of all, I'm going to take this one and I'm going to write it equivalently as a system of 2 ordinary ODEs. So I'm going to call x dot to be V, and V dot, right, is x2 dots, which is minus k over mx, right? So our initial second order ODE can be written equivalently as a system of 2 equations of first order, okay? So you can check that indeed if I do from here, x2 dots is V dot, which is minus k over mx. And indeed, this is equivalent to mx2 dots equals minus kx, which is equivalent to mx2 dots plus kx equals 0. There you go. That's your little proof there, right? Okay. So claim, okay, E of x of t, x dot of t is constant and equals E of x at times 0 and x dot at times 0 for any x of t Well, okay. Okay. Right. Okay. So let's do this. So now the energy, let's just do this first, becomes, okay, you don't have to do anything. I'll correct here. Okay. So with this new, and then I'll write it again, what I wanted to write. So now the energy, I can write it as XE in X and V equals 1 over 2 mv squared plus 1 over 2 kx squared, right? It was a square there. And now here is my claim. Now I can write it peacefully, right? So the energy along any path x of t and any velocity v of t is constant and equals the energy that is given taking this path and velocity at time 0. And this is for any x of t and v of t solution of our, let's call it 2, ODE first order system that is equivalent to the original second order ODE modeling the oscillator. Huh? Okay, so let's see proof. And now you're going to see why we had to do the chain rule. Okay. Welcome at the conservation of energy. That's what we're doing now. That's how it's called, conservation of energy. So if this is constant, this E of t is constant, this is equivalent to saying that its derivative in time is 0, right? So the derivative is 0. If the derivative of a function is 0, then the function is constant, and of course it will be the constant at time 0. Fine, okay. So we have to do dE dt, but calculated along a solution of the system, and that's the key, because otherwise we don't get anything. So this will be what? Will be dE a dx times dx dt plus dE a dV times dV dt by the chain rule. So what is this? Okay, so dE dx, remember E, here it is, right? This is the function E that depends on 2 variables, x and v, right? So dE dx is 1 over 2, right? I'm going to write it in really, right? So that's dE dx, and then times dx dt. Where do I get dx dt from? Oh, I'm going to get it from the equation, right? X dot is dx dt. So if you want dot, okay, it's the same thing with dx dt, just to make sure that you guys understand, right? So this would be times v plus d dv. Oh, so this is 1 over 2m times 2v, right? Times dv dt, which is minus k over mx. Oh, okay. So there you go. So this is kxv minus kxv. So it's 0. Ta-da! So this means, right, that d dt along any path that fulfills the system, in other words, any path that is a solution of the system, is 0. So this means, this implies that E of x of t, v of t, will be a constant for any t. Okay, so no matter what t is the same constant. And nobody, you know, is, it could be, I could choose t equals 1, but usually we have the initial conditions given. So that's why I put a t equals 0. There you go. That's it. And welcome to the first encounter with the idea of energy, right? Well, at least if you didn't do any physics. But, right? So what this says, what we will say about this, we will say that, so the total energy that's the lingo now, the total energy E, okay, is conserved, that's how we use this, by system 2, okay, or by the system that is associated with, right, okay. We also say that this function E of x and v, which was defined as 1 over 2 m v dot, right, so whatever, v squared plus 1 over 2 k x squared, is an integral of motion for 2. Yeah, so it's about how we talk about these quantities. Now, why is this an important thing? Well, there are two ways to look at it. Okay, one way is to reduce the system. So I'm going to write it again here. Okay, to one equation. So we know that this is, so this is system 2, and we know also that this guy, okay, is a constant, right? So let's call this constant h, right? And this constant, okay, rather than E of x. E of x and v is the function. H is a constant, could be 1. I'm just choosing, I'm just talking like about the level set, right, of this function. All right. Well, so these two guys are hand in hand. Any solution of system 2 will have, you know, this d dt along that solution being 0, or, you know, E of x and tv of t along that solution being a constant. But this allows us to take from here, so just take this relation and say, oh, so from here I can say, for instance, that I can solve for v and say, well, v will be plus minus root of, I'm solving for v, 2h minus kx squared, right, over m, I guess, right? I hope I did it right, okay? Where h is a constant, okay? So h is in R, all right. Oh, but if v is this thing, then I can go with this relation, but x dot equals v. So together we're going to end up with that x dot equals plus minus root of 2h, I'm going to write it nicely, minus k over m x dot, right? Or if you were confused about what it is, you know, so this is just a first order ODE. Okay. So in other words, using this integral of motion, we reduced our system of two equations to one equation. So this is a first order ODE in X, just in X. There is no V in it. So in principle, we can solve this for X of t, and then use, let's call this one star for V. Okay, so let's call this one star here. Okay, I'll do it with green so you see it. There you go. Okay, so this, the presence of an integral of motion essentially allows us to reduce the number of equations. From 2, I reduce it to 1. And this is because I'm allowed, you know, I just substituted, if you want, the velocity in terms of energy, total energy, which is a constant, and this displacement x, and then I just substitute it. So there you go. The integral of motion allows to the reducing the number of equations, right, in the system. So that's one advantage. All right. But there's not the most interesting one. The most interesting one is the one that is coming, actually. Okay. So this is, if we're doing only techniques, and I would call them analytical studies, like, man, I'm good at solving ODEs, so, give me the ODE, reduce it, and, I'm not really thinking what the meaning of it is. It's just, I'm going to do the algebra and the calculus on it, whatever, right? Okay, so there's the advantage of having an integral of motion is when it allows you to, reduce the number of equations and really, get on the job, like, okay, now I'm going to write this as a, so I can go further with this one here. So what did we have, so we had dx dt equals plus minus root of 2h over m minus k over mx squared. And because I was very good at calculus, I remember that this is a separable ODE, right? Or I was good at the ODE course. There we go. Equals dt. Remember, h is a constant fixed somewhere, is the total energy in the system. And then, we can do integral, right? And basically end up with something like, oh, integral from 0 to x of, I have to change the x to some other letter because that's why we're mathematicians. Let's say s plus minus root of 2h over m minus k over ms squared. This would be, right, t, okay, so yeah, x of t, this would be t minus 0, okay? So let's say 0 to t, and here we have to do from x, let's say x0, right? x0 to x of t. Hope you guys are with me, right? So I just put the 0 there for you to see that actually is an integration, but we don't need it, it's just t, right? And then we solve here and we find the x. Of course, this is a kind of, it's absolutely correct. The annoying part is the plus minus one, but then we observe that this is an even function. So we are doing just on the plus side, and then we say on the minus side is whatever, right? And we're done. But that's not something too satisfying for someone who's looking for, to say something qualitatively about the problem, okay? So it's correct, okay. So here I'm opening item number 2. So that's if you want advantage 1, okay? So let's say use of integral of motions, okay? So use of integrals of motions 1, okay? That's just 1. Okay, let's see, use of integral of motion 2, okay? At least for this system, it's not always like this, but for this system, okay? So remember we said that E of X and V, this quantity, okay, is, we called it H, and this constant, right? And it depends on the constant being the value at initial time and velocity, right? The initial time of displacement and velocity. Okay, so something, I could represent this stuff in a plane, and I would get probably some curves of these level sets, right? So if I'm doing this job, I could say, look, I'm going to take this plane, and maybe you've seen it before in your ODE class, but you didn't quite know why it's useful. So here is X, here is V. And I'm going to draw these level sets, some level sets of this function. So for instance, 0 corresponds to h equals 0, right? But then if I'm doing, let's say h equals 1, All right, there you go. Good. So this would be for h equals 1, right? So this green thingy is 1 over 2 mv squared plus 1 over 2 k x squared is 1, right? Well, I'm doing it circle. I shouldn't do it circle, huh? As it's an ellipse actually, right? So these are, so let's take, for example, that's the best actually. So let's say that m is, does that one change anything? So m is 2 and k is 4, okay? So then I'm gonna draw this, so it's v squared plus 2x squared, right? So these are the level sets I'm drawing. In 0 is still 0, but then, okay, so let's say when v is 0, okay, so some ellipses here, right? So let's take h equals 2, and then we would have 2x squared is 2x is plus minus 1. So let's say this. And then v is plus minus root 2. So okay. Okay, now I'm going to draw it. Okay, let's hope it will make it a nice ellipse. Okay, no. All right. Let's try again. Still wants it as a circle, but I don't want a circle. Okay, here. I don't want a circle. There you go. Yeah, okay. So this is h equals 2, okay? So in other words, is v squared plus 2x squared equals 2. That green one, okay? And I can do one with light blue. Let's say do it here. Okay, so let's say this is h equals 3, okay? So this is the curve, okay, right? So I can represent this orbits in the xv plane, right, as the level sets of the energy function. And you're going to say, so what? Yeah, I'll do it again on the next page and you'll see why so what, okay? It's quite cute actually. So I'll do it in 3D, okay? So here I'm going to do first the axis, and that's what I'm going to finish with today, okay? Okay, let's just try again. So this is an axis. Well, actually, I can do it full. Okay. Okay. And then this, and then this. Okay, so these are the 3 axes. And now I'm going to call them X, V, and time. So the vertical is time. Okay. And now I'm going to draw those guys. So h equals 0. I'll do it in red actually. Here, I'll do it in red here as well. So it's consistent, okay? Yeah. I'll do it here. H equals 0. Okay. So this red one is a solution for which x and v are staying 0 at all times. There is no motion. So this is the solution that corresponds to h equals 0. Okay. Now for the one corresponding for h equals 2 was an ellipse there. So I'm gonna try to make it here something, okay? Okay, so that's what I see in the XV plane, right? But now, what is this actually on the time axis? What does it do? You know what it does? At all times, it moves on a, oops, on a nice cylinder. Okay, so here is the cylinder. And what the solution does, here I'll do it with dark green, no, with light green, I guess. So it will do something like, I have to be careful because of the, so let's say it cuts here and then it goes up. Okay, so it goes, okay. Something like that. What do you think, huh? You see? That's what it does in time. It goes up that cylinder. And when we look down on this XV plane, we see the circle. So actually, we know a lot just looking at the plane of what is going on with this solution. We know a lot. We know that it will never go to infinity, right? And of course, we can relate it to what is happening in the physics with our oscillator, if we really want to, right? So on purpose, I did that x equals 0 there, but we cannot because the oscillator is just, we see just the, you know, the displacement. We don't really see the velocity, right? But I'm coming back here, okay, so where is it? Here, that's the ellipse for h equals 2, right? It's a perfect ellipse, okay? Just take it as an ellipse. Here, I'm trying again, okay? Maybe I'll do it with something. Yeah, good enough, right? But it has to be centered, right? So that's h equals 2, not 0, right? That's the one. And now we know, okay, so there is a maximum distance that this spring would reach, and that distance, the velocity is 0. And then from there, so here I'm going to write here the system as well. Hey. Oh, come on. Sorry about this. Right? That was the system, right? So when V is positive, by the way, when V is positive, we have that x dot is positive. So dx dt, if you want, is positive. So x of t is increasing, right? So when V is positive, x is increasing. So it should be that way. And I hope that my picture, yeah, okay. So my picture maybe is wrong here. It should be, okay, let's try again. So I have to be in agreement with what's going on with the signs. I'm getting there. All I'll do, I'll just change the direction, right? So it's like this. No, it was good. Why did I change it? It was absolutely correct. Yeah, because in the back, yeah, there you go. It was good. There's nothing to correct here. In the back is coming back, right? So in the back is coming back. Right? So that's how, because that's what we see. Huh? Yeah, it's good. Okay, so once again, right? So there is a maximum distance where the velocity is 0. Then, you know, it picks up when it reaches the equilibrium position, right? The rest position, if you want, the velocity is maximum. So in other words, when this spring is coming back, it will pass here with max velocity, right? And then it will go and it'll reach again, you know, an extreme position where the velocity is 0 and it turns around, right? But I don't have to think about, you know, I mean, I don't have to make a diagram of the spring, and I don't have to make a diagram in 3D. It's sufficient to look at these profiles, you know, these level sensors drawn in the XV plane to understand what is going on, right? So that's where the importance of the XV plane and the energy conservation is coming in, because we're drawing these nice pictures here, right? These level sets with what is going on just from the energy. So I said H equals 3, right? So these are all level sets of E of X and V, right? So in other words, they're 1 over 2 mv squared plus 1 over 2 kx squared equals different h's, okay? Now this xv plane has a name. It's called the phase plane, and is the plane where we represent the unknowns in our ODE system, if you want, right? So there you go. Okay, so with this being said, I guess I'm gonna stop here, and next time I'm gonna introduce some definitions with the phase plane and first portrait and what is going on, okay? So there you go, welcome to the world of nonlinear dynamics, although this is linear dynamics, what we did today. But yeah, it's starting, right? So this is, you know, this is the simplest and one of the most important examples that one has to start with, this harmonic oscillator. And you can see this is a completely different way to look at the set of solutions. Compare it with, you know, x of t is a cos omega t plus phi naught, okay? Which one is more interesting? I would think that the drawing is more interesting. I always like drawings, so it's just maybe just my preference, you know, but rather than seeing a formula that doesn't talk to me, you know, it's what is behind it. And there are beautiful stories about systems where, you know, sometimes we can put our hand on the solution, but it's so uninspiring and so not talking to us, you know, like what does it mean actually, you know, behind sine and cos and ln and whatever, what do you want to say there, right? So there you go. That's it's the beginning of that. That's what they're going to do in these lectures further. Okay, guys, so with this being said, I'll see you next time. Good luck in doing your assignment. Okay, and yeah, so that's that. Okay, so there you go. Okay, so see you later.